Today is our third day of faculty development program. So, on behalf of our institute, Dr. Bapuji Sawanke College of Engineering and Technology, I just welcome all the participants. Firstly, I introduce our today's session leader. I just introduce him shortly. Today's session leader is Dr. D.S. More, sir, HOD of Virgin College of Engineering, Electrical Department, and his bachelor and master degree passed out from Virgin College of Engineering. Also, his PhD completed from IIT Bombay. And his today's topic is electric vehicle and motor drive. So, I request you, sir, please start the session.
Okay, thank you, madam, for introduction. First of all, I take the opportunity to express my sincere thanks to the management of Bapuji Salunke Institute of Engineering and Technology, Honorable Chairman Abhay Kumarji Salunke, then Secretary Shubhangi Gaude Madam, CEO Kaustubh Gaude, particularly the Director and Principal of the Institute, Birdi Sir, and Suhas Sapate Sir, Dr. Suhas Sapate Sir, Coordinator of this, Professor P.P. Bhatt and Professor Narke Sir. So I thank all the people for giving me opportunity to interact with the technical community to deliver the expert lecture on electrical vehicle motor drives. My flow presentation is particularly one minute. My flow presentation is first we introduce importance of battery operated vehicle, what are driving factors for this. Then in general, battery operated vehicle, though your topic is hybrid, I am fully concentrated on the battery operated vehicle. And for this, the battery operated vehicle, we are using four types of motors possibly. One is PMSM, other is BLDC, third is switch reluctance motor. These three motors, construction, operation, and control, we'll discuss on this. And finally, we can make the conclusion of this. So let us start with our battery vehicles. We have seen that there are so many brands. Every car manufacturer has come with its model for a electric vehicle, and the market is picking up because of one is technological advancement is there, positive change in customer perception, government is giving more subsidy, strict environmental norms, and because of production volume is increasing, and definitely the cost of battery operated vehicle will be equal to a IC engine counterpart. So we have seen that what are driving factors particularly increase the penetration of battery operated vehicle, and one important first is policy and regulations. Okay, we are having a strict environmental norms particularly for these cars, and also government is giving subsidy particularly for the purchase of these EVs. Then we have seen that fuel economy, basically battery operated vehicle running cost is less as compared to our fuel cars, maybe a diesel or the petrol cars. Emission standards are raised. Then some cities we are not allowing the diesel cars. Also financial, we are already discussed, financial incentives are provided, and also the city access restrictions. Some of the cities we can't run the diesel vehicles. So these are the reasons. Because of that, our electric vehicles are increasing. But now we are having some concerns from customer point of view. Now EVs are available with a much, maybe more than 250 to 300 kilometer driving range. That was the concern earlier, but now EVs are available more than 300 kilometer per charge. Then cost premium, earlier drives cost, earlier car cost was more, now it comes down. We require, if you want to travel a long distance, we require infrastructure. Maintenance of this also is a infrastructure, lack of infrastructure. And one of the hurdle is time required to charge the battery. Okay, so now chargers are available. A normal charging we require 7 to 8 hours, but fast charging that will be completed within 20 to 30 minutes. Now, if you see the just electric powertrain, uh, particularly drivetrain in the EV, a major we have seen that the battery pack, a battery may be a 48 volt or 72 volt battery we are using for this. Then we require a charger for the charging of this main battery. Then we require one another battery for control of the EV. Maybe we require this 12 volt battery for AC as well as electronic control of these lights. All these we require a 12 volt battery. So from higher voltage battery, 48 or 72 volt battery, we are just charging the 12 volt battery through a DC to DC converter. So the purpose of this DC to DC converter is to charge a 12 volt battery, and this 12 volt battery is required for all electronic control, AC. Then we are having a power steering. For all that we require this 12 volt battery. Then conventional, whatever this main battery, we are given a motor we are using. We have seen that 4 types of motors are possible. Induction motor is there, but major use we are having a PMSM, permanent magnet synchronous motor, then BLDC, SRM. These motors, for that we require a particular converter. Converting DC into AC is required in this case, and that is purpose. So this is the major blocks you can call it drivetrain components, particularly for the EV. Any questions, madam? Hello, am I audible? Okay, okay. Now same whatever we have simplified block diagram for drivetrain for EV is given. This is a battery pack. Then we are having a converter. We are just represented a power electronic block converter. Depending upon motor, the converter will change. For PMSM, we require an inverter, whereas SRM, we require a particular specific type of converter. So converter construction or its topology will change with the motor. We are having 4 types of motor we can use. Then we are having only a single speed gear, and then differential, and whatever is connected to the wheel. So this is a general block diagram. Now, if you go for more detailed block diagram of this battery EV, so it can divide into 3 parts. So if you see the block diagram, so upper part, if you see it here, what I am showing here is a electric propulsion subsystem, where whatever electrical power is converted into a mechanical power and given to the wheels. So in case of electrical propulsion subsystem, we require a power converter which converts the battery power into a variable voltage, variable frequency, that we can call as a power converter, which converts battery DC power into a variable voltage, variable frequency AC power is to be supplied to the motor. So we require a control of power electronic converter. So this is a electronic controller, electric motor. Then we require a mechanical transmission and wheel. Now this second part is our battery. So energy source, this is the main battery, and we require 2 battery subsystems. One is a battery charger. This is onboard, you can call it onboard battery charger, and one we require a battery management system. Okay, so battery should not overcharge, battery should not undercharge, and so many other protections required for the battery that will be provided with the battery management system. So second block we are having is energy source subsystem, where we are having a battery, then battery charger, and the battery management system. Whereas we require auxiliary power, that may be 12 volt DC supply is required, that will be obtained from main battery as we discussed just now. So from main battery, we are obtaining charging the 12 volt battery, and this 12 volt battery, particularly this auxiliary power supply, we are calling it, and this auxiliary power supply will be given to a power steering unit as well as temperature control unit and the lights. So this is a particularly the block diagram, particularly for the EV. Then what are the possible options? Motors, possible motor drive options for EV. We have listed 4 here. Induction motor drive is also there, but efficiency of induction motor drive is less as compared to other drives. So use may be restricted for the induction motor, but majority we are using the permanent magnet synchronous motor drive, brushless DC drive, and some cases a switch reluctance motor drive. So in our present lecture, we are discussing 3 motors and their controls. First motor we are discussing is the permanent magnet synchronous motor and its control. Second is BLDC motor construction, its operation and control. And third is switch reluctance motor, its operation and control. So these motors we can study one by one. Before going to these motors, okay, selection of particularly drive, which motor we can select. So drive means it will come motor, converter and control. So this particular combination of motor plus converter for controlling the speed of the motor and controlling the control unit of the drive, that overall we can call as the drive. And selection of drive for EV, there are various factors. We are just listing these factors. First factor is efficiency, cost, weight and cooling. So we have to consider this, what is the efficiency of overall, cost is there, weight and the cooling. Then another point is a performance point of view. What is the maximum speed possible, reliability and the fault tolerance. Second is power rating and vehicle acceleration time. So all is based on these requirements. If you want a high acceleration time, then maybe a EV may be a costlier as compared to a normal EV. So here these are almost 7 to 8 factors. Based on that, a motor for EV is selected. Efficiency, cost, weight, cooling, maximum speed, reliability, fault tolerance, power rating, and vehicle acceleration time. Now let us start with our first motor, and the first motor is the permanent magnet synchronous PMSM motor, permanent magnet synchronous machine. In short, we can call as PMSM and control. If you here we have just shown the three-dimensional picture of the motor. So we are seeing that we are in inner rotor and outer stator. So the stator of the PMSM is similar to our conventional induction motor. We are having the slots in the stator to accommodate the three-phase winding, and this winding is a three-phase distributed winding. Whereas on the rotor, we are having a permanent magnets on the rotor. So here we don't require the power for our copper losses in the field windings are absent. So definitely our efficiency of permanent magnet synchronous machine is higher as compared to a field wound synchronous machine, because we replace the field winding with the permanent magnets. So here we have shown that our magnets are on the surface of the rotor, and so it is called as a surface mount PMSM. And here we are having a three-phase stator windings in the stator. Now, why we are going for synchronous machine, and that for that we are taking example. In all houses, we are using a motor for lifting the water. Let us assume that we are having just 1.5 kilowatt motor. Induction motor, its efficiency is 75%. And so input power required for 1.5 kilowatt induction motor is around 2 kilowatt. So we are taking a low capacity is a 75%. If high capacity for lower capacity approximate full load efficiency 75%. So input power required is a 2 kilowatt. Is around 88% or 90%. And then input power required is just 0.704 kilowatt. So here, if you replace our induction motor with PMSM, then definitely we are saving up around 296 watts. And if one city we are having if these motors are 1 million motors are there, then we see that how much amount of power we can save. So this is the benefit that efficiency of PMSM is better as compared to induction motor, and that's why we are going for the particularly battery operated EV. Definitely we are going for a permanent magnet machines. So here we have just given a sketch. This is our permanent magnet. So this is the permanent magnet we are having. Basically, quarter portion of the machine is so. This is the stator winding of the machine, and this is the permanent magnet. So this particular machine, if you complete this, it will have a 4 pole. So on the rotor, we are having a 4 pole. A counterpart of that we have shown is the. It is again a synchronous machine, but field wound synchronous machine. And here we have shown the 1 pole here again the same. We are having a 4 pole synchronous machine. And here we are interested in the whatever the flux in the air gap. And a flux in the air gap or MMM due to winding is proportional to its area. Here area of cross section of winding for MMF. But in case of PMSM, the thickness of the thickness magnet strength is proportional to depth or the thickness. And here because of that, a particularly magnet size required will be less. So the machine will become compact, reduce the size, increase the efficiency in case of a PM machine as compared to a field wound machine. Now let us go for what are 4 poles. These 4 poles are mounted on the rotor surface here. So NS, we cut the rotor portion and we put the magnet inside the rotor. So it is we can call it the inset. Inset PMSM. Here we can call that's why it is called as a buried PMSM. So we are in 2 types, particularly 3 types of the PMSM based on the how the magnets are kept on the rotor. So let us consider particularly first case, or before going to that, we are using the permanent magnets, and permanent magnet has the BH curve. Okay, normally magnetic material BH curve is in the first quadrant, whereas particularly for permanent magnet material BH curve is in the second quadrant. Here whatever we are, and here H particularly is the curve H we are having for this magnet, and this H will be produced because of the MMF of the particularly stator winding. And we have seen that at no load there is HM is very less. So this will be our open circuit operating point of machine. As load increases, our value of H produced by the stator winding increases, and our normal operating point will shift to this. Suppose due to some whenever short circuiting the stator takes place, then definitely we are having a large in that case, and then our operating point may shift to the uh, to a lower value. Any question on this? This is the BH curve of PM material. Normal operating point we are reaching that. Under short circuit conditions, then operating point should not go into the third quadrant. If operating point goes into the third quadrant, the magnet will demagnetize. So that our interest is what we require, the value of Hc, intrinsic force, that value of Hc for the magnet should be very high. Based on that, so we are having BH curve. Based on the BH curve, we are having the various types of magnetic material. If you take a curve, if you see it here, a particularly a curve, here we have seen that our residual flux is very high, 1.3 Weber per meter square, or we are having, but particularly H is very low, and that will be just a 50. So this will be a machine will be subjected to demagnetization, and that particularly we are having a alnico. Similarly, B we are having again that H value is very less. If you go for C onward, that our H value is H and B values both are going to increase. So our best material for the permanent magnets is the G and F, you can call it. G is a centered NDF. F is our centered SMCO. So these two, okay, sintering is the process by which magnets are made. So we are having these two materials, particularly a sintered SMCO, samarium cobalt, and sintered neodymium iron boron. These use for. So is it clear? So we are using these other materials may not be used, but only we are using sintered samarium cobalt and the sintered neodymium iron boron. These two iron boron we are using constructing in the machines. Now here we have just given you when these materials will be developed. So if you see it here, so latest material NDFEB, we have seen that our SMCO 2:17, they are developed in 1984 and 1980. So the two materials where it will give that also here BH max, that is energy kilojoules per meter cube, and the HC intrinsic force, particularly how much kilo ampere per meter. Now here we are given just of the magnet material. So magnet volume and BH max. So minimum volume is our NdFeB, neodymium iron boron. After that we are having a samarium cobalt, then we are having ferrite, and then we are having alnico. You see that the when we are using a good quality, when Hc is high and permanent magnet will be less. And whenever we are having a minimum, we can use compact machine. Also, operating temperature is a very important, and we are going for a class A particularly for this. Problem is that the corrosion of the magnetic material takes very fast, and for that we have to plated the magnets with nickel plating. Now here we have shown just the rotor part of. So any question on permanent magnet pH characteristics and which material we can use for construction of the permanent magnet synchronous machine? We are using neodymium iron boron and samarium cobalt for the uh, construction of the machine. Now here we have shown the rotor portion only. Our stator is the same as slotted stator. We have not shown here. Just we have shown the number of rotor poles or magnets on the rotor. We are having four magnets, NS, NS. We are having, and here we can say that we are in the D axis and Q axis machine. And here one important thing is magnets act as an air gap to external flux. Whatever XD and XQ is because of the stator flux. And for stator flux, this magnet will work as an air gap. So whether we are going for whether we are going for a direct axis or quadrature axis, the air gap is the same to the external stator flux. our external flux we are calling as a stator flux, internal is the permanent magnet flux. But for XD and XQ is because of the stator flux. And for stator flux, we have seen that the magnet will act as a air gap. So here along direct axis and quadrature axis, air gap seen by the stator flux is same, and because of that we can have a XD will be equal to XQ. And as air gap is high, our reluctance will be high. That what we are having. And here whatever this torque load I have mentioned, this torque load will be as so the torque front and the whatever we are having the speed. So torque is proportional. Now here we are having the another rotor construction we have taken for PMSM is the interior PMSM. So magnets are, these are the four magnets. They are built in the rotor, and we are on D axis and the Q axis. Here physical air gap is same. Physical air gap is same, but actual air gap along D axis will be more because magnets will be coming. This magnet for external field will act as an air gap. So along D axis we are having width, whereas along Q axis our air gap compared to earlier here along D and Q axis, Q and D axis air gap is same, but here along D axis air gap is more and along Q axis air gap is less to the stator flux, and because of that XD will be less than XQ. XQ will be more, XD will be less. And here small air gap is present, because of that armature reaction is there. And once you are knowing here when XD and XQ are different, then definitely we are having one torque that present that we can call as a reluctance torque. So here net maximum torque in case of this PMSM will offer at 90 degrees, but here Tmax particularly for this will be a less than 90 degrees. So permanent magnet motors will just take a brief review. So we can use this SMCO, samarium cobalt, or NdFeB magnets. And when you use this particular material, PMS, permanent magnet material in the machine, then a size of the machine will become compact, a rotor diameter will become less as compared to conventional induction motor, and as rotor becomes smaller in diameter, inertia becomes less, we get a faster response. Whereas the higher efficiency, because reduction in the field copper loss is absent in the permanent magnet synchronous machine, so higher efficiency, and because of that higher torque per ampere. So here PMSM, we replace the field winding with the PMSM. Now here we can, one method, we are going for the open loop speed control of particularly the PMSM. So here we are having the open loop. So again here almost V by F ratio is to be maintained constant. So normally in case of induction machine or PMSM, we have to maintain V by F ratio constant. So if you go for V by F, that ratio we have to maintain constant, and because of that flux in the machine is particularly maintain constant. So here lower frequency we have to apply the voltage. So here we are having two commands are given. So one is the voltage, how much voltage, depending upon frequency or voltage will change. So we apply a variable voltage, variable frequency to the induction synchronous machine to control the speed. During braking, here we have shown the dynamic brake. This is not the diagram for EV, a conventional. We have shown it supply, three-phase supply, diode rectifier. We get a DC, VLC filter, and this. If we apply just a variable voltage, variable frequency, we wait of PMSM. So for the variable frequency, we require a PWM inverter in this case. So here, in case of these machines, we are in two operating speed. We can call as a torque is constant or flux is remaining constant. So phi of that flux remains constant, and this region, because of that, torque will remain constant. So up to base speed or the up to rated speed, torque of the machine remains constant, maximum torque remains constant, and that's why it is called as a constant torque region. Above base speed, above rated speed, if you want to increase the speed, it will be becoming region. In case of with the help of a particularly vector control. So here, whatever we are having a simple, this is a simple scalar control where we can just vary the voltage and frequency applied to the PMSM. So any question on this? So we discussed the construction of PMSM and the speed control of PMSM with a variable frequency control. Now let us go for vector control, and for vector control we require a transformations. Okay, so we briefly discuss the transformations. So three-phase quantity can be converted into a two-phase. So here we have given a three axis: A axis, B axis, and C axis. So this is a three-phase quantity. These axes are stationary, but the quantities of voltage, current, or flux that will change with respect to time on this. And then we are in the two axis that will be 90 degrees to that. So we can convert a three-phase quantity or three-phase supply into a two-phase. And here angle theta is between the ABC, that is ABC, and you can QD. So that angle is theta between the two reference frames. And three-phase quantity can be converted into a two-phase. When theta is 0, particularly we get a constant matrix. So we are in the three-phase supply that has been converted into a two-phase. So here if you just have a three-phase supply, then apply this transformation, then we get a two-phase. So here this is three-phase sinusoidal voltages, three-phase balanced sinusoidal voltages. Apply transformation, we will get a two-phase balanced. Frequency will remain same. Input frequency of three-phase and two-phase is the same. This transformation, reverse transformation, is also possible. Here we have shown three-phase is converted into a two-phase. If you see it here, then another reverse is also there. If input is two-phase, then we convert into a three-phase. And for that, this is the input is two-phase QD0, we can call it, and output is the three-phase. We use this particular transformation to convert a two-phase into the three-phase. Again here, our input output frequency is the remaining same. Now we are going for one another transformation. So here we have shown the two frames. So this is one QS and DS. Superscript S here stands for the stationary reference frame, and whereas we are having the synchronously rotating reference frame that is represented QE and DE. So and DS. Okay. And quantities from stationary reference frame will be converted into a rotating reference frame. And for that, we have to use these equations. We require sine theta e and cos theta e. So here, if you see it here, So these are the stationary voltage, d-axis voltage and q-axis voltage. From stationary, you can get the q-axis and d-axis in the rotating reference frame. And for that, we require a sine theta e and cos theta e. Similarly, here from rotating reference frame, we can shift to the stationary reference frame, and that also we require sine theta e and cos theta e. And the sine theta e and cos theta e sinusoids we can call as the unit magnitude vectors. So here we require, so whenever we are having now transferring quantity from stationary reference frame to a rotating reference frame, when the frequency of this particularly currents on the stationary reference frame and a speed of rotating reference frame, if both are same, then AC quantity on stationary reference frame, AC quantity on stationary is the DC quantity on the rotating reference frame. So that is the importance of this. So when you transfer quantity from stationary reference frame to a rotating reference frame, frequency and rotating speed are the same, then AC quantity will be converted into a DC quantity. We can utilize that. We can see now this is a particularly a phasor diagram of a synchronous machine in a synchronously rotating reference frame. We have shown the D axis and the Q axis. Okay, these both axes. This is a diagram of synchronous machine. Phasor diagram of synchronous machine in the synchronously rotating reference frame. So DE and QE axis are moving at a speed given by omega E. Along D axis, we are having a magnet flux. We represent this. And flux produced by the armature that we can call as phi A, and resultant flux we can call as phi S. If our magnet flux is along D axis, then EMF induced because of magnet flux is along QA axis, and this will be given as omega E phi F. So this will be our voltage induced in the machine. VF we can call it, voltage induced in the machine. Whereas VS is the voltage applied to the machine, and angle between the back EMF of the machine or voltage induced in the machine and the supply voltage, that we can call as the load angle delta. So here we have shown the load angle delta in both cases, and we have seen that phi A and IA will be in phase, and we are depending upon inductance, we are having a particularly the power factor angle of PMSM in a synchronously rotating reference frame. Rotating reference frame, and here two fluxes, flux they should be always quadrature to each other. Here we are having a slightly higher value that we can discuss. So any question on this phasor diagram of PM synchronous machine? Am I audible? Hello? Hello, sir. Am I audible? Yes, okay. So any questions you can ask. Then now we are having two operating modes. One out of that is true synchronous mode. True synchronous mode means machine is work like a synchronous motor. Okay, its load angle will change, and that we can call as a true synchronous mode. So if you see the open loop control of the synchronous machine, this in that case PMSM, as load increases, the load angle will change. That concept we can call as a true synchronous mode. Whereas we are having that we can call as a particularly a self-control mode. So there are two modes of the operation of a synchronous machine. True synchronous mode means machine is working like a conventional synchronous machine. As load increases, there will be change in the load angle. The speed will not change. The speed will remain synchronous, but as load increases, the load angle will increase. That we can call as a true synchronous mode. Whereas another mode we can call as a self-control mode. that resembles to the DC motor. So here, if you see it here, we are having a diagram of DC motor. Okay, a two-pole DC motor. We are having a armature winding, and then two-pole we are having this. So our flux produced by the magnets or the field winding is horizontal. It will be represented as psi f. Whereas we have seen that flux produced by the armature is always along the brush axis. So here we are having two fluxes. One is the flux produced by the permanent magnets, and other is flux produced by the armature current. And flux produced by the armature current is always along the particularly the brush axis. So here, if you see here, we are having a two fluxes which are quadrature to each other. Here we are having a main flux psi f, you can call it, and a flux because of armature current psi a. They are always quadrature to each other. These fluxes are not directly not affecting each other, and that control you can call as a decouple control. So there is a inherent decoupling between the armature flux and the DC motor. In case of DC machine, and this is obtained in case of PMSM, that will be a self-control mode, and that is nothing but also we can call as a vector control. On the permanent magnet, two pole are on the rotors, and we are in a three-phase stator. So three-phase stator will produce a rotating magnetic field that will be psi A, and field will produce the flux that is psi f. As our rotor is moving, these both quantities will be move at a certain angle. Now here position of psi A depends upon the how we apply the current to a three phases. And we try to maintain this angle by controlling the inverter, by knowing the position of permanent magnets. So psi f, by knowing the psi f, we control the inverter such a way that psi f flux because of PM and flux produced by the armature, they will remain always at the 90 degrees, similar to a DC motor, and that operating mode we can call as a self-control mode. Now already we are going for a vector control. So what is the concept of vector control here? So we want to maintain the two fluxes at a 90 degrees. What are two fluxes present in the PMSM? Two fluxes present in the PMSM is one is whatever flux because of armature current. That flux you can call as here psi A. This is psi A is the flux produced by the armature current. So our interest is we have to maintain main PM flux and the armature flux always at the 90 degrees. So this is our we are having. So because of this main flux, our induced EMF will lead by an angle of 90 degrees. Is it right? This will be a EMF induced because of psi f, and that is VF. We can call as induced EMF omega E into psi f. That will lead the psi f by an angle of 90 degrees. So this will be our induced EMF, and our current will be 90 degrees to psi f, so it will be in phase with Vf. So in case of vector control, our IQS, this current we can call as a active component of the current, and here ID, that is the reactive component, a flux producing component. Here IQS we can call as a torque producing component of current, and here flux producing component of current we make it 0. IDS is 0 means we are not weakening the flux in the machine. And so here also vector control is also called as a current we are forcing in phase with the back EMF. So here we are having this induced EMF and the current, they are in phase, and because of that we can call as an internal unity power factor for this. We are having a psi 8 stator flux corresponding, we are having a psi s. So this is a phi, and here del will be the one of the same. So in case of vector control, our strategy is we want to know the rotor position, flux position. Based on that, switch the inverter so that armature flux will remain 90 degrees. In other words, we sense the back EMF machine and inject the current in phase with the back EMF of the machine. That technique we can call as the vector control. Is this clear? So in case of vector control, we find out the back EMF and inject the current in phase with back EMF. That technique we can call as the vector control. So here for vector control, so here we have shown our a complete block diagram for vector control of PMSM. So here we are having a speed reference and speed feedback. So we are having a position sensor on the motor shaft, and based on that we can sense the position of the motor and the reference speed we compare, we get error. And this controller is the PI controller. It is also called as a speed controller. And this output of speed controller you can call as a torque reference. And in this case, our torque is proportional to the current, and that is why we can call this as a current reference. And this current will be a active component of current. So output of PI controller is IQS. That will be a particularly we are having a active component of current. This is we are operating in the synchronously rotating. So this is in a synchronously rotating reference frame, two phase. From that we convert into a two phase stationary, and from two phase stationary to a three phase. So once we know these two values, we get a three sinusoidal currents. Is it right? So we get a three sinusoidal currents, I star, ID star, IC star. We use a PWM inverter with hysteresis current controlled PWM, and we force the same current into the motor. So that technique we can call as a vector control. We get a better dynamic response in case of a vector control of this. So any question on vector control of induction motor or vector control of synchronous machine? Any question? Now let us go for, so this will be a particular data Tata EV specifications we are given. And Tata EV, they are using the motor is the permanent magnet synchronous motor. Maximum power is 142.68 bhp. Motor power is 106 kilowatt. Battery capacity is 40.5 kh. And range we are given 465 kilometer. Lithium ion battery we are having. A normal we are having 7.2 kilowatt charging, 6 hours for we can call a slow charging. And for fast charging, we require almost 1 hour. So this will be a specifications of particularly motor specifications for uh, motor and the battery capacity used in Tata EV. So this is one motor we have discussed. Any questions? So this is the PMSM. Efficiency is high. We are having a simple control, or but normally all these motors, all these EVs, we are going for a vector control of this. So any question? Am I audible? Hello. Yes. Okay. So any question? I am expecting at least one question from audience regarding the PMSM drive, which we are using for the let us have any questions. for next machine, we are going for a BLDC motor drives, brushless DC motor drives. We are having a motor and controller. So only BLDC motor is not useful at all. We require both the converter and motor. So PMSM also we require a motor and converter. Only motor is not okay. What are the motors we are discussing? They are always come with a converter control and motor combination. Whether we are having a PMSM, BLDC or SRM, all the motors they will come with motor, controller and the converter. So here this particular shows the converter and controller of the motor, and this is the motor. Particularly we are having a BLDC. In case of BLDC features you are knowing, we are calling as a brushless DC motor. Why we are calling as a DC motor? Because its performance characteristics is similar to a DC motors, but it works on AC supply. We require a motor and converter combination is required. We can't use single motor. A variable speed application, well known. You are now that BLDC fans, single phase BLDC BLDC fans are available. It is a permanent magnet. We have just shown the same diagram here. So three-phase winding on the stator. We are having this winding is a distributed, but whenever winding is distributed, then winding pitch winding we can have a full pitch or the short pitch. So I think everybody knows what is meant by full pitch winding and short pitch. Whenever electric angle between the two coil sides, if I just take the pen, and this is our one coil side, or here, okay, 1 minute. Erase. Oh, I'll draw it here. It is okay. So we are having some problem. I'll try to here. Whenever we are having a coil and two coil sides, we are having. Okay, and if the angle between the two coil sides is 180, it's called as a full pitch winding. And when the angle is less than 180, it is called as the short pitch. Okay, so PMSM we use a short pitch winding, whereas BLDC we are using the full pitch winding. Full pitch winding means electrical angle between the two coil sides is 180 degrees. So one prominent difference between the BLDC and PMSM is, in case of BLDC we are having full pitch winding, whereas PMSM we are having a short pitch winding. So here we have shown the winding. This winding is a full pitch winding. Basically for this motor, if you see it, we are having number of poles are 6. Is it right? And one pole corresponds to a 180 degrees. So total electrical angle will be 180 into 6. Whereas here we are having a 6 slots. Okay, so that particularly we are having, so 180 into 6 divided by 6. So here angle between one slot is coming 180 degrees, between the slots is 180 degrees. So we are in concentrated winding is here, but it is a full pitch winding. So very important thing in case of BLDC motor is the winding is the a full pitch winding. Okay, so here we have shown the stator winding. It is a 3-phase. This may be 1-phase, second phase, and the 3-phase. It is a full pitch winding we are having on this, and this is the 6-pole rotor we have shown. Now here one prominent here is our back EMF. In case of our PMSM, back EMF is sinusoidal. Induced EMF is sinusoidal. But in case of this BLDC motor, we have shown the induced EMF when we rotate the rotor because of the PM flux. The EMF induced in the stator winding will be a trapezoidal. What shape of this will be a trapezoidal? We show a 3-phase voltage is induced when we rotate the rotor of the motor. Then we get this particularly voltage. That voltage you can call as a trapezoidal voltage will get. Around 120 degrees we are having a constant voltage. and next 60 degrees the voltage will change from minimum maximum to minimum, and next 120 we are in constant negative voltage. Again 60 degree change from minimum to maximum again. So this particular, and it is a concentrated full pitch winding, and because of that pole pitch to pole arc. So this pole arc and pole pitch, this we can call as a pole arc and pole pitch. That ratio is almost one, and because of that we get a particularly the trapezoidal back EMF. So main reason for trapezoidal back EMF is concentrated full pitch winding, and pole arc to pole pitch ratio is high. Okay, so it will be almost 95%, and because of that we get a three induced voltage, and these voltages will have a particularly the uh, and whatever electric phase shift between the voltage is 120 degrees, but we are having a trapezoidal trapezoidal back EMF. And when back EMF is trapezoidal, it is not necessary to apply the sinusoidal current. And in that case, so we apply quasi square wave current. So here, if you see that when our back EMF is non-sinusoidal or trapezoidal, then no point for giving a voltage current to the winding is a sinusoidal. We give a quasi square wave current for A phase. Whenever back EMF is constant, positive current. When back EMF is changing from positive maximum to negative maximum, we don't apply any current. And when back EMF is negative maximum, we apply the negative current. Okay. So in case of BLDC, we are applying the a quasi square wave current. Just a minute, I'll just come. दाराला नाहीये, दाराच्या वरती. ठीक आहे, हे राहू दे. चालेल, ठीक आहे, ओके. For currents of the quasi square wave currents, when back EMF positive, apply positive negative current. Whereas in case of PMSM, we apply here we apply a quasi square wave current. In case of PMSM, our back EMF is sinusoidal. Here back EMF is trapezoidal. That is the difference. So here we have seen that we have to sense the back EMF and apply the current. When back EMF is positive, we apply positive current. When back EMF is negative, we apply negative current. And for that, we require a position sensor in the motor. We know the magnet position, so we require a position sensor. And based on that, we control the inverter so that we apply the quasi square wave current to the motor. Okay, so here we have shown it here, represented as a VC, and which devices. So here invert. So they are marked as per conducting sequence. This will be a first leg. In the first leg, we are having the two devices, Q1 and Q4. Second leg, we are having Q3 and Q6. And third leg, we are having a Q5 and Q2. These devices, which devices we can turn on so that we can apply. So here Q1 is on and correspondingly Q6. So here we have seen that we are at a time only two phases are on, not three phases are on. So here one upper device and one lower device will be on. Which devices will be on for these currents, we have given it here. So Q1, Q6 is there, then Q1, Q2 is there, Q2, Q3 is there. So devices we are giving it here, and these devices are conducting particularly for almost 120 degrees. Each device is conducting. So one device from upper and one device from lower always make the parties make the particularly a pair. So Q1 in with a Q1 either Q6 or Q2. These two devices will be working. So Q1 we are having a Q2 and we are having a Q6. Okay, so each device is conducting almost for a 120 degrees. So here we can have a current control also. So one current device, a lower devices, whatever this Q4, Q6 and Q2, we can operate in the, so these devices will be on for 120 degrees, whereas these devices will be turned on and off based on the value of the current. So we can regulate the current. So here Q6, Q2, Q4, we are operating in the chopping mode, or we can have prevailing mode, whereas this will be a devices, particularly upper devices will be on a continuous. Now, why we are calling BLDC? Because here we have seen that only two phases are on at a time. Okay, so 2 ID into VC, that will be a total power input. That will be torque into omega. And now if you get it here, so twice, if you just simplify, T will twice ID VC by omega m. So we replace omega m by omega r. Actual rotor speed, this is synchronous speed. Based on that, P by omega r. Okay, we are having. So a relationship between omega r and omega m, we put this, and with the help of that, we'll get this expression for torque will be P ID VC by omega r. And here VC is nothing but a K omega r. We can take it. And here we can say that VC, that is the back EMF induced, that will K into omega r. Omega r get cancelled. Here we see that torque is proportional to ID. Torque is proportional to this DC current. Torque is proportional to the DC current, here DC current, and it is similar to but here we don't have brushes. Whatever this inverter, it is working as a commutator as compared to a DC motor. So why it is calling as brushless DC motor? Because performance characteristics are similar to a DC motor. Torque is proportional to ID. We can control the speed by controlling the voltage. Okay, and here this will be inverter will work like a commutator, and that is why we can call this as a brushless DC motor. Of PMSM and BLDC. So our sinusoidal stator winding means EMF induced is sinusoidal, and it is a distributed winding, short pitch distributed winding. It is a full pitched concentrated winding in case of BLDC, and because of that, we are having a trapezoidal EMF, or rectangular, or EMF is trapezoidal. Here EMF sinusoidal. Okay, and here whatever current we have to apply a sinusoidal, and here we are getting that motor is compact motor is BLDC as compared to a PMSM. Torque ripple will be higher in case of BLDC, but less in case of PMSM. So cost will be higher for PMSM, less will be for BLDC. And this will be our closed loop control of BLDC. So for closed loop control, this will be our inverter. We have to control this. And here we are taking the speed position sensors we are using, and that is the Hall effect sensors we are using. They will find out whether N pole is there or the S pole is there. Based on that, they will develop a current template. A decoder will develop a current template. Current template means unit magnitude current, 120 degrees positive current, next is 0, then 120 negative of magnitude. That current template will be generated by the decoder. So purpose of decoder is to generate the current template based on the position sensors. Based on the position sensors, we have to generate the current template, and that job is encoder. And its magnitude of that current template, 120 degrees positive, 120 is negative. That is the unit magnitude we are having. Here again, we are having a reference speed and actual speed. G is here our PI controller, and output of speed controller is a torque reference. We can ID is there. So ID multiplied by unit this, we'll get a three current references. We sense the three current feedbacks, and then we use a hysteresis current control PWM to control the switches. That will be a control for particularly a BLDC. And we are going for applications of BLDC. Using for variable speed supplement plus we can use a servo and robotic drives, particularly in case of CNC machines. Huh? Okay. Then next question on the two motors. We have discussed PMSM and BLDC. I am expecting at least one question from audience. Any question? Hello, am I audible? Hello, is it clear? Sound is clear? Is PPTs are visible properly? Okay. Now next motor we are last motor we are covering is the switch reluctance motor that we can call as SRM. Switch reluctance motor drives. Here we have shown the particularly motor stator. You have seen it here. Particularly, we are having a stator here. On the stator, we are having a winding. So here, if you see it here, we are having a one phase winding, second phase winding, third and fourth phase. So we are having a here motor is having a four phase. Okay, we can have a three phase also, six phase also. Is it a four phase? So there is no restrictions particularly this. And here you have seen that our rotor is just a slotted laminations kept on that. And here we are having a six particularly rotor poles. So here eight we are having a stator poles, eight stator poles and six rotor poles. So it is called as 8x6 pole SRM, and number of phases are four. So it is a four phase 8x6 pole SRM in the diagram. This is the diagram of the SRM motor. Now here some silent features of this machine. Here we are shown earlier diagram is 6 by 8 by 6. Is there 8 poles, stator poles and 6 rotor poles. So we have seen that now we are having a PMSM or BLDC. Number of stator pole and rotor poles are same. In case of PMSM and BLDC, number of stator poles and rotor poles are the same. But here we have seen it here. Here our stator poles are 8, rotor poles are 6. If you see this diagram, here we are having our stator poles are 6 and rotor poles are 4. So a number of stator and rotor poles are always different in case of SRM. It is a doubly silent, means we are having a slotted structure both on the stator as well as rotor. We are having slotted structure, that's why it is called as a doubly silent machine with different number of stator and rotor poles. Other machines, if you take an induction motor, synchronous machine, BLDC, a stator pole and rotor poles are the same, but here we are having not a stator pole and rotor poles are stator. So you see that So flux produced by these two, that care we have to take. Of these two coils, so net flux will be increased. So we are in one phase, particularly total flux having a. So these are we are supply to the stator winding. A concentrated. Okay, so here we are supplying a DC current to the stator winding. One phase is excited at a time. Okay, we are having a one phase is excited. So not all phases are excited. Only one phase is excited. Hello. Okay. Yes, yes, yes. Okay, okay, okay. I'll just share it. I'll stop sharing. Okay, so I will just go once again. Is it okay now? Okay, I'll just share. Entire screen. Okay, this share. Okay. Then
Okay, sir. Right
no,
now
just see.
visible.
Is it visible? Okay. Okay. Immediately you can tell me. Okay. So here we have shown this. Is it is the slides are visible when we are talking about this slide? Okay. So now we are talking about the construction of SRM. So in case of construction of SRM, one important thing is that doubly silent structure means slotted stator as well as a slotted rotor. Uh, is it available? 1 minute. I will just take a laser pointer. So slotted stator, slotted rotor. That's why it is called as doubly silent. Here stator poles 6, rotor poles are 4. So different stator and rotor poles. Concentrated winding we are having on the stator poles. This winding we are excited with the DC current. Flux produced by upper coil and flux produced by lower coil, they should be additive in nature. Based on that, we have to make the connections. And one phase is excited at a time. Whereas your principle is rotor will attain a position where reluctance is minimum. So reluctance principle we are having. So if you excite, let us assume that if you excite a Y phase, then rotor will try to align the Y phase. We'll discuss the operation here. So let us here you consider. So here we have shown the one diagram we have shown is 6 by 4. Just we have discussed. Then it is a 8 by 6. We are having a 4 pages. And this will be a flux. One phase is excited. We get a flux pattern. So flux of one phase is not linking with the other phase. And that is why we are having a magnetic isolation between the phases. So flux of that phase will link only to that phase. It is not linking with other phase. So we can have a, they are having only a self inductance. They don't have a winding, don't have a mutual inductance. And the magnetic circuit is isolated for each case. Now here operation for a rotor will adjust such a position that reluctance to the flux path is minimum. Now let us assume this diagram here, first diagram. And if you excite, rotor position is here, let us assume that. And if you excite this particularly coil, A coil, and then we see that our rotor will have a reluctance torque and rotor will try to align the A phase so that reluctance is less and flux linkage is maximum. And here if you want to control the direction, so once commit here, then we apply the current to the B phase, then rotor, this rotor will align, and then we apply the C phase, then rotor will align. Is it right? So sequentially, we have to excite the windings. One winding we are excite at a time. So for clockwise rotation, we supply current to A phase, then B phase, and then C phase sequentially. And in case of anti-clockwise, we just change from apply to B, A, and C phases sequentially. So this is a flux pattern. We have shown it here. The flux of only that phase is linking that we have. And here we have seen that SRM cannot run directly on AC or DC bus. We have to just give a DC current to the winding for a very short duration, depending upon the rotor position. So again, the same diagram we are having. Here for one another some applications we are having in case of EV, particularly we are having a outer rotor SRM. So here rotor is the outer and stator is the inner. And on the rotor we can call as in-wheel motor. Particularly some two-wheelers we are having a in-wheel motor that BLDC, but similar we can have a option for SRM. So rotor is the outer as like our fan, and inner is our stator, and over the rotor we can have our particularly the rim of the vehicle we can put over that. So a particular in-wheel motor drive where motor is in the wheel itself, that is we can call as in-wheel motor drive. So just we have shown the flux path of this, how the flux path we are having. Now one important is that winding we are having only a self inductance, and that self inductance depends upon the rotor position. So here, if the stator and rotor poles, we have shown it here diagram sequentially. We have taken it one stator pole here and the rotor pole here, and we have shown it here. Here, if you take a stator pole and rotor pole are not aligned, which is we are having a pink color, stator and rotor not aligned. So inductance of the stator winding is very low. So that will be represented as the L minimum. Here, if you say second case, yellow case, we have seen that some part of the stator pole and rotor pole are overlapping, and because of that, flux will pass and inductance will increase. And here, if you see it, next, both stator pole and rotor pole are aligned, so maximum flux linkages, so maximum inductance will get. Here also we are aligned. Here again, the flux linkages are decreasing, so inductance is less, and here less. So one important feature of this stator winding is inductance of the winding is changing with rotor position. I want to make one statement again. Inductance of the winding is changing. Inductance of the winding is changing with respect to rotor position, and it has a two values. When unaligned inductance, that LU can minimum inductance you can call as unaligned inductance, and maximum inductance, aligned inductance you can call as a maximum inductance. So a stator winding has a having varying inductance. It will be varying from L minimum to L maximum depending upon the width of the rotor pole and the stator pole. This structure will be there. So this is the inductance profile of the particularly machine winding, and then we can torque equation we can get it. We are not going detailed derivation of the torque equation, but we can see that here when dl by d theta, whenever inductance is positive, dl by d theta, rate of change of inductance is positive, apply the current, then we get a torque. When dl by d that 0, though you apply the current, you will not get the torque. Here dl by d theta is negative, so we'll get a negative torque. So simple or torque equation we are going, torque is proportional to half I square dl by d theta. Very important term is in the change of inductance, rate of change of inductance. Is it a positive or negative? Based on that, we are getting the driving torque or the braking torque. So here, if you apply the current here, in this case, you will get a motor torque. If you apply DC current to the winding here, you get a braking torque. So that is, we are having this is the torque equation of SRM. It will be given as 1 of I square dl by d theta. Okay, you can just go detailed derivation of this. Now here we have shown the motoring torque here. This is the inductance. First diagram you see it here. Inductance profile, minimum inductance and maximum inductance. And we allow the current, positive current, DC current, when inductance is increasing, dl by d theta is positive, then we will get the motoring torque. So we get a motoring torque when dl by d theta is a positive. So this will be a torque. This will be here, though current is there, our dl by d theta is 0, will not get the torque. So torque will be obtained only when dl by d theta is changing. When dl by d theta is 0, torque is 0, whatever the value of current. So we have to apply the current when dl by d theta is changing. Here we apply it, then we'll get a positive torque. If you apply the current here, then we'll get the negative torque. So applying the DC current to the winding, we require a converter, and various converters are available, SRM converters. So purpose of converter is to give the current to a specific phase, and that we can have various types. Out of that, one or two we'll discuss here. So classic converter, then dual rail converter, converter for motor having bifilar winding, C-dump converter, and a Miller converter. Out of that, one will discuss only one simple one, that is a classic converter or the dual rail converter. So what is our so we are having seen that for each phase we are having a separate converter. So here we have shown n phase. We have shown just two here remaining in between that. So if you see it here, so one phase require two switches and two diodes. If you see it here, one phase requires, okay, one phase particularly requires the two switches and the two particularly diodes. If you switch on both these, I will just draw the here particularly this. If you switch on, if you switch on the switch S1, our current will flow like this. Is it right? Our current will be flowing like this through S1, S2. The current will be flowing like this. And when any one switch is becoming off, current will freewheel through the diode, either this or that. And so here, so we can switch on the two switches to increase the current. If you want to reduce the current, you can switch one switch. If you want to stop the current, then both switches you can turn it off. So one minute. So is this clear how we control the current? For increasing the current, we switch on a particularly two switches we can switch on, so current will increase, pass through that. If you want to freewheel the current, want to limit the current, decrease the current, you can switch off any one of the switch, either S1 or S2, then current will freewheel. When S1 is on, current will freewheel through this. If S1 is off and S2 is on, then current will freewheel through the D2. And if you want to stop the current, you switch off S1, S2, then the diodes will conduct and current will be given back to this. So this is a classic converter we can have. So, and what are the features of this? Okay, the phase can be controlled independently. That is one aspect. Device voltage rating is that of DC voltage, and our total number of switches is two switches per phase is required in this case. So this is a particularly converter we can call as a classic converter, where we require two switches and two diodes per phase. So if four phases is there, we require 8 switches like that. Now number of phases we can reduce, number of switches we can reduce if we are having even number of phases. If you are having a 4 phases, or if you are having a 8 phases, then for a 2 phase we can make a particularly this circuit we are having. So here per phase, here we are shown a 1 phase. Let us S1 is on. So how the current will flow? I will just show this dotted with this. So current will flow like this when who will supply our upper capacitor will supply the current. That is our path of current. Okay, so path of current when S1 is on. Now if S1 is made of, S1 is made of, what will happen? When S1 is made of, when S1 is made of, then we have seen that energy stored in the winding is there. So current will flow like this. It will charge this capacitor and prevail through this. So that we can have. So this will be a operation. When the switch is closed, current will increase, whatever we have shown with red path. When the switch is open, current will prevail through the diode and will charge the other battery. So that will be happening here. So it will can call as a dual rail converter. Other configurations we are not going in detail. Now, what are the advantages of SRM? So we are having that a simple and robust. Okay, that is first. One switch per phase. We have seen the dual rail. Inverter size will be small. Here, one important is that we can run the motor in both direction and break the motor in both direction. So here, braking torque we can apply by applying current here. Motoring torque we can do by applying current dl by d3 positive. By changing the sequence of applying phases, we can run in forward or the backward direction. So quadrant operation of the particularly SRM is the 4 quadrant, which will be required for our drive. Then here direct shorting is not possible, no shoot through faults. If suppose we are having a 4-phase SRM, if one phase becomes faulty, that phase can be isolated and motor can run with that. Zero short circuit current and zero open circuit voltage, that is feature of this motor. We don't require any commutator, and characteristics is similar to a DC series motor. These are some of the advantages of this. Then what are the disadvantages? We want to determine the coil inductance because the torque is depends upon 1 of I square dl by d theta, and we should know the position when the inductance is increasing or decreasing. For that, we require rotor position encoder. Accurate torque control can be problem as accurate determination of coil inductance is difficult. It is having some noisy operations and we are having a torque ripple. So SRM is having a more torque ripple as compared to BLDC, and PMSM has less torque. So if you are having the highest torque ripple is SRM, then BLDC, and then a PMSM. Now here what we have shown it is here below base speed, below rated speed, we can control the current here. If you see it here, we are controlling, maintaining the current. We can on the S1, S2 both switches here. Then here if you want to decrease the current, we turn off one switch. Again, we close both switches here. Again, turn off one switch. And here we turn off both switches so that we can give a back energy and this. So we can control the switches. This particularly operation, we can go for particularly this switch. When both are on, our current will increase. If one is open, current will decrease. Both are open, again, current will be becoming 0. So that will be this here. If you see that here, both switches will be off in this case. Here, both switches are on. Here, one switch is off. Here, both switches are on. Here, both switches are on. When current increases, both switches are on. When current decreases, one switch is off, one switch is on. Okay, so that will be a control is possible. Whenever we are operating at high speed, then in that case, duration is very small. And in that case, we cannot have a current control mode. In that case, we are having angle control mode. So our current is almost constant here, but in case of angle control, before coming to the inductance, we have to raise the current to a high value. And so here we can call this is the angle control mode where our inductance profile become positive here, but before that we adjust the current to the motor to a higher value because time available is very short as the speed is high. So this is our particularly the torque speed characteristics. This is a constant torque. Then we are having a constant horsepower, and then this is a characteristic similar to a normal DC motors, series motor. So this is the speed torque characteristics that will be suitable for our EV application. And lastly, we are going for a closed loop control of SRM. So here closed loop control, so speed reference and speed feedback. So SRM we require a rotor position feedback because we want to know the dl by d theta, whether our inductance is increasing or decreasing, and for that we should know the rotor position. And once you know the rotor position, we can also find out the speed. So speed feedback, speed reference, we can give to PI controller, that will be current reference, how much current we can apply to the phases, and based on the rotor current, okay, based on the particularly this available current rotor position, we can switch the current into the motor winding. So hysteresis current controller, so current will be maintained within this. So if you see it here, this is our hysteresis current control. Here current will be maintained within I max and I minimum with the help of the switching of the devices, switching of the converter, and we maintain the current. So this is a closed loop control particularly for SRM. So torque ripple in SRM. So main drawback of the SRM is a torque ripple, acoustic noise. And so servo applications, we are going for PMSM. SRM is not applied to, but EV, definitely the SRM has a good potential. So now we conclude our lecture. PMSM and BLDC motors most efficient, have a high power density. BLDC drives are less costly compared to PMSM drive. Induction motor is also a good candidate for EV for controllability and cost. Weight of SRM is low, reliability is high, it operates with a fault tolerance and according to the acceleration time. Its performance is better than IM, and SRM is also a best candidate for EV. So with this, I conclude my lecture. I have covered the, sorry, take 1 minute. I have covered the three motors, PMSM, BLDC, and SRM. If any questions are there, you are welcome. I will try to answer your questions. Hello, am I audible? Yes, sir. Is there any questions from your side? If you are having any doubts regarding the, so we covered three motors for the EV, PMSM, BLDC, and the SRM. Okay, induction motor is already covered. Okay, but normal candidates are the, at present we are having PMSM and the BLDC from battery point of view, because losses we want to be made less, and for that definitely we have PMSM and BLDC. So any questions, any doubts, then we can discuss. Hello, any questions? Not a single question. हाँ बोलो. Okay. Thank you for patience listening. Okay, I try my best to deliver. Maybe because of it is online. Okay, may not be a very proper way for presenting. Okay, but I will try my best. Tried my best. Thank you for patience listening. Thank you all. Okay, thank you, sir. Thank you all.